Okay, it looks like it's official. We can get going. Welcome back, everyone. So for today's class, I don't have a whole lot of announcements, and our whole goal is to finish off section 3.3. This one's a shorter one. We're starting to get going further into chapter 3, so these are not as crammed full so far. Also, we have the quiz 2 that's posted, and quiz number 2 is going to be due on next Tuesday. That's pretty much going to be our pattern through the semester. Well, any questions at all, folks, before we begin? Okay, let me first, before we just jump into section 3.3, discuss a little bit more about the ALEKS website and due dates, how to request an extension. So let me clear off all these notes. Once we finish a section, like how we finished section 3.2, I'll post a due date, or if I feel like there's a strong chance we'll finish a section like 3.3, I'll post a due date here as well. So these are the same exact due dates that you'll see in the ALEKS system. They're just duplicated down here. And if I jump to ALEKS, you see them again right here. Section 3.2b, the last half of that section, is going to be due, oh geez, here, no, that's something else, due tomorrow at 11:59 p.m. So due Friday. Any questions about that so far? Okay, now if I click on start my path, I'll just be working out those problems right here. But one thing you want to definitely take attention to when you're in ALEKS is, obviously your ALEKS grade, right? The grade for this class in ALEKS, double check so I figure, make sure that that's muted. Sorry, I know there was just a little bit of feedback there. So if I go to the very, very top syllabus, it says right here that ALEKS is worth 20% of your grade, which is definitely substantial. So if something goes late and you didn't have an opportunity to finish those problems, we are leaving some of that percentage on the table. But the good news is I will allow you to go back and complete it. And there's a couple ways that's going to happen. So back to the ALEKS. To see how you're doing on your ALEKS grade, which is 1/5 of the class, click on the menu bar right here before you click on Start My Path. And this link right down here under Gradebook, I would say that's one to definitely check out quite a lot. On the end of the week, on Fridays, I'm going to take your gradebook grade and throw it into Moodle, so you can check it in a couple different ways, but there's still some value in checking it right here. So let me click on Gradebook. Now, this is my own. I've been working in ALEKS alongside the class since I'm just trying to refamiliarize myself with the system. And it says, kind of rudely, my overall ALEKS grade is 50%. That sounds really harsh, but if I look down here, here's why it's 50%. It's always based off the sections that have gone past due. That's when the grading happens. And I only completed section 3.1a. I got to a full 100%, and I ignored section 3.1b completely, and it has 0% weight there. So from these two, my overall grade is 50%. Once the due date goes past on section 3.2, it's going to pull in 3.2a, and 3.2b, which I'm currently working on, only at 56%. So that's how your grade is going to update. It's only giving you a grade on things that have gone past due. Does that make sense to folks so far? Okay, so other thing I want to mention is, if you're going to take a look at your grades, the ones down here are the ones that you might want an extension on. Really, all you have to do is find the section you need an extension. It's this one here because the grade's low, and email Mike Jacobson at, that's a terrible at symbol, let me try again, at isu.edu for an extension. There is, thank you for spotting that. That was not going to be very helpful. Mike Jacobson, I should know how to spell my own name, but things happen. Thanks for spotting that. Mike Jacobson at isu.edu. And that's the same email address you're going to see on the very top of the syllabus. So just duplicated right here as well. And when you send that email, just say college algebra so I know which class. It could be incredibly informal. It could just be, hey, Mike, can you give me an extension on 3.1b? That's all you have to say. You don't have to give me reasons. I know life gets pretty crazy. Could be other classes, jobs, wife, kids, all sorts of things could be going on. You don't need to tell me about your personal life. unless you think it might be helpful. So you can just simply send off a really fast email like that. I'll go into the system and put in an extension so you can continue working on that section there. So really the due dates, they're only for pacing. If something goes past due, well, I didn't get any of these points, but I can still make it up for full credit. Does that make sense to everyone so far? Okay, let me put this in our current notes today, just as a reminder on how to get an extension. So I'm going to just go and drop it. Oh, geez, where should we put it? At the very bottom, probably be the least intrusive spot. Okay, other thing I want to mention, there's two ways that these are going to be extended. On a person-by-person basis, just send me an email if you need to go back and work on something. But I'm also going to do blanket extensions for the entire class. And this is essentially how it's going to work. When we get closer and closer to this date right here, Monday, oh geez, it's going to be held on Tuesday. That's already a typo. How about we fix that right here and now? I've heard most of my classes are on Mondays, so I think that's where I got mixed up. Exam 1 will be held on Tuesday. I'm gonna have to fix the rest of them, but I'll focus on just correcting this one now, just to not mix up people in the class. That would mix me up. Okay, so let me start over. When we get closer and closer to this date, Tuesday, September 18, our exam 1 date, probably around this week right here on the Tuesday of that week, I'm going to go into the ALEKS system and just request an extension on everything that's going to be on exam 1. That way you can go back to the ALEKS and practice everything that you need to practice, shoring up all those sections. Yeah, go ahead. Oh, I didn't move the actual date itself. Thanks for spotting that. So Tuesday is on the 19th. And anything that's been a revision is in red, is usually why you might see a red here and there. Hopefully not too many revisions. And I'll just make a note to myself. I think now I need to finish or revise these other exam dates. This one is Tuesday, October 17th. Again, sorry about that. It's correct here from the syllabus, but I just screwed up at the start of the semester, it looks like. So again, think of the due dates that you see in ALEKS. They're for pacing purposes, so we don't get too far behind, too inundated on trying to catch up. If you're getting everything done by the due date, you're doing extremely well and staying caught up with the course. If there's a couple hard topics that you just didn't finish off, or if life got a little busy 1 week to the next, there is always opportunities to get extensions. And the last punchline was, before exam 1, a week before, everything will be opened up for exam 1 topics. So you can really work on everything, reviewing and getting caught up. When we go down to the final exam, way down here, oh, I had a Tuesday there. That's the one I must have got right, December 11th. Let me double check the calendar here. No, that's December 12th. Jeez. Always frustrating when we get typos in, but I'll make sure to correct them as needed. Sorry about that, folks. Okay, December 12th is our final exam. I'm going to have to double check these dates. But that's how our ALEKS system is going to work as far as getting extensions and things like that. Any other questions, folks, about ALEKS or otherwise? Okay, well, where we're at right now, we're in section 3.3. Let's jump in and take a look. These sections are going to be a little bit more focused than like we've seen before. The other sections were kind of getting everyone on the same page. They had a lot of introductory topics and definitions. But here in this section, the main topic is going to be about rates of change and when functions are increasing, decreasing, minimums and maximums. So we're really just analyzing graphs, seeing what we can learn from those graphs. Starts off with a really technical definition and immediate graph problem that we're going to solve at the same time. Let me zoom in on this just a touch. So it says here, a rate of change describes how an output quantity changes relative to the change of an input quantity. So if we're looking at this graph here, the outputs are things like 0.5 going off to 1. And as we move from 0.5 to 1, the outputs are the height of this graph getting larger and larger. One thing we might want to know is, what is the average rate of change over interval? And it says here, the average rate of change between two input values is the total change of the function values divided by the change in the input values. That's saying a lot. So we're going to do an example right away to see what they mean by that. Let me highlight a couple things. Between two input values, on this problem, we want the average rate of change from 0.5 to 1. Those are the input values on this particular problem. They say next is the total change of the function output values. Well, the function output values, let's put this in green, is what we're meaning by this stuff, the f of x2 minus f of x1. Let me make sure I can highlight that appropriately. So once you know what your inputs are, you can calculate your outputs right there and just calculate that entire quantity. So let's visualize this on our graph here. The inputs are x equals 1 and x equals 0.5. We always think of the larger one as being the x2 value going down below. So our x2 is this one. x2 equals 1 in this problem. And our x1 value is going to be the lower value, 0.5. So if you keep that pattern, x2 is always the larger value, then up above, we'll have f of x2 and f of x1 keeping that same format. So let's find those output values on the graph. x1's 0.5. Keep in mind, we're visually estimating, so I'm not trying to get a perfect number, just as close as I can. But at 0.5, here's the height of the curve, and the output value is right here. This is f at 0.5. And it looks like it's about 0.4 altogether. Does that make sense to folks on that output? Awesome. Well, for x2, we have a value of 1, so we go right over here, go way up till we hit the graph, and that particular point is going to be f at 1. We go all the way to the left here. Here's f at 1, which is equal to, I'd say, about 0.7. Looks like what it falls on the graph. If you were doing this as a quiz problem, you called it 0.6, this one 0.5. That's completely fine. They're well within the ballpark. If you call this one 70, then that's when we were going to be wildly off. So now I had 2 points in blue. We want the average rate of change. Let's add one extra thing to the graph to just kind of say, what is it we're calculating when we calculate an average rate? So I'm going to put in a new line here. My line is going to go between those two outputs, this point and this point. So there's my line. And I don't know if that's the best color. Let me try and make one that stands out a little bit better. Let's go for, how about this color? Oh, geez, I keep picking colors that are close to the graph. This one will be different, I promise. Last try. It stands out a little bit better, I think. Maybe not the best. But there's our line. It connects through this dot and this dot, which is these values up here. And I meant to have those in green just to tie them with the definition. And we call this the secant line. When we calculate the average rate of change of a secant line, we're just finding its slope. And so that's always a really good idea to keep in mind. The average rate of change is equal to m, which is the slope of the secant line. So if you're calculating a slope, really the denominator looks the way it should. It's just the numerator that looks weird. But keep in mind also, y is also equal to f of x. And so you could have just said that this is equal to y2 minus y1 divided by x2 minus x1. In other words, you're literally doing the same exact thing of calculating the slope of a line, but it's this line, the secant line. That slope is going to be the average rate at which the function increases from here all the way to here. So that's the main idea of this kind of problem. All we have to do now is crank it out. Any questions first? Okay, so we're doing what's a glorified slope. It doesn't look like a slope up here because it's f of x2, but that's just an output value, y2. These are those exact outputs. And so if I use this format, or if you use the slope formula, you're getting the same exact work. So let me go down below and actually calculate it. I'll put here average rate of change is equal to, and this is a good thing to put in because that is what you're calculating. It's a reminder. But if you want to paraphrase this massively, you can just call it M. It's nothing but a slope. The way we're calculating it is f of x2 minus f of x1 divided by x2 minus x1. So really, we're pretty far along this process already. Once you found the outputs right here and you knew what the inputs were, we'll put in the denominator, x2 is a positive 1. Then the formula says minus x1. x1 is a 0.5, so throw that in. And denominator's done. That's just going to come out as a positive 0.5. For the output, f of x2, well, x2 is 1. We went up here, and that's the value here. F of x2 is going to be 0.7. Then it'll be minus f of x1. x1 is 0.5, so we went here, up, and we found the value is 0.4. So that's our f of x1, 0.4. All that's left now is calculate the numerator, denominator, and simplify. Numerator is just a 0.3. Denominator is 0.5. If you multiply this by 10 over 10, this becomes exactly 3/5. So what it's telling us is, as we go from 0.5 to the new location at 1 for x, the graph is increasing on average by 3 units vertically for 5 units horizontally. So that's our average rate of change on this graph here. Any questions at all, folks, on that computation? Okay, main takeaway of doing this by graph is we're just figuring out what the definition is even saying. This is the picture that goes immediately along with it. And the way I solved it was I wrote this first. This is actually a tremendous strategy in any math class. If you know you're about to use a formula, I encourage you, write it down. Try to write it down cold. Don't look it up. Put down as much as you can. And anything you've forgotten, then double check your notes, see what the rest is. If you challenge yourself to do that every single time a formula is coming up, I promise you, you will memorize that formula, and it's going to be a massive support on the exams. Well, any questions at all, folks, then, with finishing off example 1? Yeah, go ahead.
So then, with the denominator in the equation, you have up there the 1 minus 0.5. So it's 0.05, and then you would divide. You can just divide those two together to get 3.5.
Well, what I did here was I multiplied the top by 10 and the bottom by 10, just to move the decimal over.
Gotcha.
You could have put it, say, right in the calculator to get a decimal answer. I'd say the reason I did it this way is more often than not, Alex wants the fraction if it can get it.
Okay, so that's the preferred answer in Alex.
Yeah, usually the fraction in reduced form. Other problems in Alex are just going to say, calculate it, approximate to so many decimal places. And on those, I would have just stuck this right into a calculator and got a decimal answer. Other questions at the moment? Okay, it's nice having a graph for this, right? Because we get our function values immediately. So on the next one, we're going to take away the graph and see how we can do it just going blind. Really, that's the major formula. And here's how that next exercise goes. We have a function g that's provided. It's a degree 3 polynomial. My voice is dying, sorry about that. And it says find the average rate of change of g on this interval from -2 to +2. So here's what I'm going to do first on this one. Let's just remind ourselves what we're doing. Average rate of change. If you like, you can call it a slope m, or just write it out. I'll highlight this in yellow just to indicate that's what we're going to call it this time. The computation is, well, I'm not going to say f of something like we did up here, because the function's g this time. So we change the name and say g of x2 minus g of x1, divide the whole thing by x2 minus x1. So that's a format. Every time the instruction says find the average rate of change. Yeah, go ahead.
You already said, but like, also, like, this is just the exact same as y2 minus y1.
It is, yes. And the correspondence is, no matter what, This is function notation, but it's the same as saying y equals g of x. So you can always think of it in those terms as well. Other questions about that so far? Okay, so now next thing we have to do in this is start filling out the denominator first. I'd say is a really great choice. But to do that, we need to know what is x2 to begin with. Has anyone spotted the value of x2? Exactly. It's stated differently, right? They gave us a closed interval, but there's a lot of formats you could ask this kind of question. Sometimes it says literally x 0.5 to x equals 1. So it's a little bit clearer. That's your x2, that's your x1. But when you see it in this format, then yeah, absolutely. This right here, oops, let me try again. This right here is x2. And this one right here is x1. So I'll plug the positive 2 first, then the negative 2 right after. I'll put an extra parenthesis just to be mindful of that additional negative sign we have to navigate through. Next, well, the g function is right here. So we have to calculate, I'll do it over here as scratch work on the margin, g of, let's do this one first, g of x2. G of x2 becomes g of, we go back to what x2 was, it's a positive 2. Now to calculate g of positive 2, notice we're just jumping around the paper. We go right here where the g function is defined. Everywhere you see an x, throw in a 2. So this is going to turn into 2 cubed minus 3 times 2 squared plus 2 times 2. You could throw that all into a calculator if you like, but good practice doing it by hand. A little bit faster for me, not pulling up a calculator. 2 cubed is 8. 2 squared is 4 times negative 3 is minus 12. And the last term will give us plus 4. So this is 12 minus 12. It equals exactly 0. That means 0 goes right here in place of g of x2. Look all right so far? Awesome. Then we do it again. Don't forget to copy that additional negative sign. Okay, there it is. We didn't forget it. Next, go g of x1. I'll do it on the margin again as scratch work. Look up your x1 value, negative 2. Look up the function and throw negative 2 inside. So this will turn into negative 2 power 3 minus 3 times negative 2 squared plus 2 times negative 2. Then down below here, let's crank it out. Negative 2 cubed is negative 8. Over here, negative 2 times negative 2 is positive 4 times negative 3 is negative 12. And this becomes a minus 4. And that's our function so far. So it looks like negative 24 is what that'll tally up to. So negative 24 will go here. Extra parenthesis just to be mindful of the double negation. Now, this is pretty much the hard step. If this was a problem on, say, exam number 1, I might give this 5 points. And right to here, that's definitely 4 out of 5 points. That's the whole punchline of evaluating the function, knowing what your x values are. Last thing to do is just crank it out, simplify whatever you have. But that is really pretty much where the college algebra ends. Rest is arithmetic. Any questions, folks, with the college algebra portion? Okay, let's get a value out. This is negative of negative 24, so it equals positive 24. Down below, this is really 2 plus 2, so positive 4. And so the average rate of change of this function g is 6. As we go from negative 2 to positive 2 on that graph, we're expecting it to rise by 6 units per every 1 unit. Well, that's the process, folks. Same as what we did before, but this one's nicer because it has a picture. So this one is very helpful for understanding what the average rate of change does. But some problems will also look like this one here. Other questions or comments? Okay, we're doing a little bit more with this function just for the sake of it's in WebAssign. So I felt like we should answer this question as well. Let's also get the x-intercept and y-intercept. Sorry, question first? Oh, that came from right here in the numerator. It was the negative of negative 24, so I converted to a positive. The 24 came from right here as a negative value. So we did g of x1, we threw it right here, GX1 comes out as a -2, and then we just did all the arithmetic right here. Once we got -24, it went back up to that location. There's really lots of arrows on how this goes. Think of when you do this kind of college algebra work, it's a lot of substitutions all over the place. X1 got substituted for -2. Then right here, we cranked out all of this stuff and got our value. Other questions so far? Okay, thank you for asking that question. And now that you've asked that question, I notice I do have a typo on this. When I said g of x1 equals -2, it's not quite what I meant. I should have said g of x1 equals g of -2. Really, all I was substituting out was the x1 value like that. So sorry for that confusion right there. Other questions or comments at the moment? Okay, well, let's do a review topic on intercepts, just for the sake of finishing off this problem, see what will happen next. Oh, can't do that. I'll leave that right where it is. Let me just scroll to about right here. We want to know x-intercepts and y-intercepts on this graph. And let's start with the easy one. Y-intercepts are terrific when it comes to a function. There's exactly one y-intercept, and it's really fast to compute. So let's start with the low-hanging fruit, and let me put in a quick note. For a y-intercept, I'll usually abbreviate int dot for intercept. Set x equals 0. So in our problem, we go to the function, we're throwing in 0 there, and here's how it's going to work. We'll go g of 0. That means we're plugging 0 in everywhere x occurs, but x occurs on every term. That means the whole thing is 0 altogether. You'll get 0 cubed minus 3 times 0 squared plus 2 times 0. Whole thing becomes 0 altogether. That means we're done on this one. We have a y-intercept. And I'll state my answer as an ordered pair, an actual point on the graph. So I'll say here, the y-intercept equals, take the x-coordinate that we set to 0, there it is, and then take the output, that's the y-coordinate, which came out as 0. So the graph is going to go through the origin. That means it's both an x-intercept and a y-intercept all at the same time. Any questions first? Or any questions, folks, on doing this one? Okay, so y-intercepts are great. Sorry, go ahead.
Two questions. So with the 0 that you plugged into the formula for g 0 equals 0, what did you get the 0 from again?
Whenever you do a y-intercept, it always means the x-coordinate is 0 by definition.
Okay.
So really, if it says y-intercept, that's always a foregone conclusion. You have to throw that 0 in right there.
Okay.
That makes sense with that? Gotcha. Other questions at the moment? Okay, now let's switch this around. This is the one that's less fun. X-intercepts can be fast, but it depends on the function. Sometimes there's some extra work to do on them. And this is one of those cases. So for the x-intercept, set, well, let's pause right here. For a y-intercept, you set the opposite coordinate, x to 0. So by that logic, if you're looking for x-intercept, you set the opposite coordinate, the y-coordinate 0. So we'll set y. Remember, y is an entire function. It's g of x. So set y equals to g of x equals to 0 and solve. So right where you see that g of x, a 0 goes right inside. An x-intercept means the output value is 0. We want to know what inputs led to a 0 for the output g of x. So I'm going to copy this equation with a 0 right where you see the red dot. 0 equals x cubed minus 3x squared plus 2x. Now, let me do one additional thing on my notes. I try to write my answer so you can just follow left to right, reading those equality signs. But whenever there's a lot of stuff just around everywhere, I will do this to box out my answer just to make sure we know where the answer actually is. And this was just how to start it. Well, down below, we're solving that equation. It's not the world's best equation, But the one tool you always have is factoring. In fact, that's what we were doing last classes. We solved these kinds of equations just by factoring alone. And the best way to start this is, notice X appears on every single term. That means you can factor it out, and that's probably the best first step. Factor out X, then go line by line. X cubed goes X squared. From negative 3x squared, you get minus 3x. And from the 2x, you'll just get a plus 2. If you distribute it back in, we'd have the original thing, x cubed minus 3x squared plus 2x. So we're back in business. Next thing, we'll factor that polynomial and get 0 equals x. X squared can be split up as x and x. We have a positive here, so both signs are the same. And a negative here says, well, signs have to now be negative signs. So we'll throw them in, minus and minus. And because 2 is prime, probably our best choice should be 2 times 1, right? Could be other stuff, but that's a great place to start looking. 2 by 1. And now here's my check. I'm trying to hit negative 3x, and the way you get there is x times negative 1, negative 2 times x. But those do end up as a negative 3x, which tells us, yeah, that's the correct factorization right there. What any questions, folks, on doing the factoring portion? Okay. Now, here's the big punchline to why we like factoring so much. You have something times something else resulting in 0. And for real numbers, x had to have been 0. Let's start off by saying x is 0. Or if you plug a positive 2 in here, it's 2 minus 2 for 0 again. The equation balances as 0 equals 0. Or there's a third possibility. Plug a positive 1 there. You'll have 1 minus 1 for 0, and the equation balances. 0 equals 0, because that 0 would multiply everything throughout. So the solutions are 0, 2, 1 for that equation. So in other words, if g of x equals 0, x is 0, 2, 1, and we can now say the x-intercepts are these. The second coordinate is always 0 when you give an x-intercept. So if you start off like this, that's not a bad idea. It's like safety in a certain sense. You have the second coordinate y set to 0 on all 3 of them, and the first coordinates go 0, 2, 1, so 0, 2, 1. Those are all 3 x-intercepts finally. Notice the y-intercept here, 0, 0, matches with this one. If you have 0, 0 as an x-intercept, it's automatically a y-intercept and vice versa. But these two are new ones. These are other places where the curve will cross the x-axis. Any questions at all, folks, on finishing off this one here? Yeah.
You said for x-intercepts, the y value is always 0.
Exactly, yeah, that was this right here. Other questions so far? Okay, well, that's average rate of change. And one of the things we want to look at with average rate of change is, why do we care? Why is average rate of change so important? And the idea is because of something called a difference quotient. That's a weird object. When we say difference quotient, we mean that fraction right there. And I reduplicate this graph to just give some feel for why do we calculate a difference quotient? Why would we care? So for this graph, let's say the horizontal axis represents time. And the vertical axis, mispronounce that, represents distance. Say distance from home. Then that would mean ignore this thing beyond 0. That would be negative time, which may not make sense. Let's say it starts right at 0. You leave for work. And as you're driving, as time goes to left to the right, you get further and further away from work. And maybe you forgot something at home, like your cell phone or something like that. Then as time moves forward from here, the graph is going down, which means our distance is getting smaller. We're getting closer to home until right at time 2, we remerge right back at home. So that could be a time and distance graph. If that's the case, slopes on this are velocities. Just like if you're in your car and you're looking at your speedometer, it's telling you how fast you're going at any certain time. So if I can do a slope that goes like this, that would be awesome. If I could calculate the slope of this line, it would mean at this time, looks like 0.7, we are going, whatever the slope is, miles per hour. Sorry, say again? It's exactly what a derivative is, yes. And so this difference quotient, it's really about calculus. If later on in a calculus class, I'd say, take the limit as h goes to 0, you will find the slope of this line. But we can't do that in this class. One thing we do have is that line. We can do a secant line, and those are going to be the ones that we calculate. So let me show you what it would look like on this graph, and then we'll practice calculating a couple of them. Does that sound all right to folks? Okay, riveting stuff. Let's see how it goes. So yes, this is a calculus topic. And if you know you're going into calculus, one of the hardest things about getting started is all the algebra. There's a lot, and we'll see a little bit of it just today. So in order to get the instantaneous velocity, we instead do something like this. Suppose that's our x value. Matching that one, we'll put in an x plus h. Let's say it goes right here. Here's x plus h, gives us another point on the graph. If I draw a line that goes through right here, that's not exactly the line I would want. The slope would be close to what we would like, but we would like for h to get smaller and smaller and smaller, which makes this point go closer and closer to the left, giving us instantaneous velocity, or the derivative like you mentioned. So how can we do that? Well, we just need a slope. And the slope here would look like this once again. M equals, in the numerator, we would take f of x plus h minus this function value, f of x. In the denominator, we would have to take the x2 point, x plus h, minus the x1 point, which is just x. But then this would simplify to m equals f at x plus h minus f of x, all divided by h, which is this thing right here. So the h we think of as a quantity that's getting really, really small. And as that happens, these points get closer and closer to each other until we're calculating the slope of a line based off one point, which in algebra is supposed to be impossible. But with calculus, it can be obtained. That's the secret ingredient. And so all we're doing today is just practice working with it. If this problem comes up on an exam, I will print this. So it's not a formula you have to memorize. It's something that will come up, and we just have to be familiar with how to work with it. This graph here is my attempt to say why you might care. What is its value? Because we're going to do something that's pretty computational right here. Any questions, folks, before we give it a try? Okay, so I looked at the problems that you'll be getting in ALEKS, and to me, this is a pretty moderate difficulty one, and this is the more difficult one on part B. So let's give part A a try. It says calculate the difference quotient. And if this was a real exam problem, I would give you this as well. I would just state what the difference quotient is in the middle of that exam. So now let's give this a try. And by the way, if I remember this right, let me double check. I wrote this quiz the other day. Hey, yeah, it's a quiz problem. So we're doing something heavily similar to what you'll be doing on the quiz as well. Oh, sorry, that's quiz number 2. I'm going to have to revise that. But we're about to do something similar to quiz number 2. And whenever that happens, sometimes I go like this. Quiz. Doesn't mean I'm going to give you a quiz, but if you come back to these notes, it's just my way of highlighting something that is very similar to an upcoming quiz. Well, let's give this a try, folks. If you want to calculate the difference quotient, well, you just do this numerator right here, divide by the denominator of h, and you're in business. So let's start this off. In fact, let me highlight slightly differently. I'm going to do this in blue and this one in green. So let's write out f of x plus h, then minus f of x. The entire thing is divided by h. Well, first thing to do, let me put in a big fraction bar. Right here where it says f of x plus h, we go to the f function and we're going to throw in x plus h here and here, anywhere x emerged. So this turns into -3x plus h squared. So I put x plus h right here, putting it in blue because we're just doing that part of the difference quotient. Then it's 4 times x plus h, so plus 4 x plus h. And then finally, I'll copy the -1. Now I'm down to this segment. I'll just insert the negative sign, make my fraction bar a little bit longer. I never seem to make them long enough. And now we're inputting in f of x. One thing that's super easy to miss here is f of x has 3 different terms separated by the plus and minus. We do require a parenthesis right here to let the negative sign distribute through. And then just copy in the function. If it says f of x, that's f of x. So -3x squared plus 4x minus 1, all divided by h. So there's our difference quotient. And one thing we do have to do is now simplify this whole thing. Any questions at the moment, however, writing this much down? Okay, to me, this is the hardest spot because the difference quotient is kind of a big fraction when you throw everything in. And we have to be very familiar with how the function notation goes, how the x plus h's emerge. But once we get to this stage, all we're doing is expanding everything out, collecting like terms, and simplifying as much as possible. So starting with this, I'll leave the -3 as it is. We have to FOIL x plus h squared. I'll put it out in here in the margin. X plus h squared comes out as x plus h times x plus h. And if you FOIL that out, you get x squared plus xh plus xh again plus h squared. Those 2 terms combined, so that comes in as a 2xh. So back in blue, I'm working on this portion and I get a -3 still multiplying x squared plus 2xh plus h squared. Over here, we might as well distribute 4 through and get plus 4x plus 4h. And then finally, -1. Now we're way out here. All I want to do next is distribute that negative sign. So that negative sign is going to flip the sign of everything in that group in green. So it becomes +3x squared minus 4x, and then +1. Well, we did it, folks. That's our entire numerator. It's a lot of stuff, right? But sometimes in these math classes, college algebra, calculus gets a little bit worse. Stuff gets a little bit hairy on the paper. Word of advice is go slow. It's almost more about accounting than it is math. Keeping careful track of all these terms and dropping them down in a careful way is sometimes the bigger challenge with all this stuff. And now that we're this far, let's combine what like terms we can combine. I have a 4x. It eliminates with the -4x right away, so that's a like term pair. So far, I have nothing to combine with 4h, but the -1 cancels off with a +1. So that's a few terms gone, a little bit of a simplification. Last thing to do is we'll distribute that -3 in and do our final cancellations. Any questions at all, folks, to this stage? Okay, yeah, go ahead.
So with the -3x squared plus 4x minus 1, that's in that initial equation you have. Where did that come from? Again, it was just the x value. Is that
You're talking about this group right here?
yes?
It came from the f of x right here. So it was really just this f of x in the formula. And what's nice about that formula is you're just dropping that original equation right in every single time. Other questions about that? Okay, well, let's crank this thing out. Down here, -3 is going to distribute into that group. So it's -3 x squared minus 6xh minus 3h squared. Just skipping to the ones uncanceled, there's still a 4h. And there's still a 3x squared. All of which still divide by h, but you'll know you've done this right when that h will always divide out evenly. Some way, somehow, we have to be able to make that happen. If I can't make it happen, well, there's been a mistake on the problem. But notice negative 3x squared cancels with positive 3x squared, so that's a help. Next, all terms in the numerator involve h, so you can factor it out and get h multiplying negative 6x minus 3h plus 4. The factoring step is just a way to cleanly see that now the h from the denominator cancels with the h we just factored out. So that's gone, and the whole thing turns into negative 6x minus 3h plus 4. So that's finally our difference quotient for that polynomial right there. Think of it as a challenging algebraic kind of problem where you do function notation, lots of math to try to simplify it down. And everything above is the geometry of why it's of interest, why we might want to calculate those kinds of things. What other questions so far, folks, on that one there? Okay, well, my next one is the challenge one. We definitely ought to do that one. Would you all agree? Okay, let's give that a try. Difference quotients with polynomials, not the worst thing in the world because, well, there's no fractions. That one's a little bit worse. That's obviously going to involve some fractions. So I'll show some strategies on how to get through it as well when we do this one. First, we're doing the difference quotient, this thing right here. So I'll copy it in as my first step. We need to calculate, let me make sure my colors are the same. Let me go blue first. G of x plus h minus, and let me fix my penmanship here, minus g of x, all divided by h. Now, my first strategy here is the g of x plus h is going to be a fraction. And so now I have a fraction in the numerator of my overall fraction. You can simplify that a little bit to make it easier to work with by taking the h out of that denominator. Write it as 1 over h, multiplying g of x plus h minus g of x. This step is not required, but I truly feel like it makes it just much more easy to manage. Otherwise, you'll have a tall fraction that you're working left to right in. This is saving paper, if nothing else. So once we've done that, I'm going to plug in the value for g of x plus h. This turns into first 1 over h is multiplying. We go to our function g, and everywhere where I've highlighted in yellow here, throw in x plus h. So we'll get x plus h divide by x plus h minus 1. Then minus. Now we're done with that portion. I copy the negative sign. G of x, that's just that whole thing. So we copy that in. X over x minus 1. Well, we've got it, folks. That's the difference quotient. Now it's all about simplifying. Any questions or comments at the moment? Okay, so my strategy on simplifying this is we need to add up these denominators. I didn't leave enough space, so I'm going to put in a new line. I'll make my fraction bars extra wide so we can put in all the required stuff. And it will look like this for the moment. The difference quotient is 1 over h multiplying. First, I'll copy this in, x plus h. Put some parentheses around it. And parentheses around x plus h minus 1. Now I'm copying in the negative. Same deal with the new fraction, or the second fraction, x, and then with parentheses, x minus 1. If this had two terms, like x plus 1, I would have put parentheses around it as well. But as a single term, parentheses are not needed on this one. Now, next thing we do is, to add up these two fractions, we just insert what's missing in the denominator. Anyone see what's missing where that red dot is? Sorry, say again? Close, it'd be just that x minus 1 altogether. I think you might have said that the first time, sorry. So yeah, this one's missing the denominator of x minus 1. Here we go, we just throw it right in. You have to put it in top and bottom so it can cancel off. We're not damaging equality that way. Then we do the same exact thing over here. This denominator is missing x plus h minus 1, so throw it in below and above. So it always looks worse before it gets better, but trust me, this is starting to get better. It's cleaning up at this stage. I'm going to put in an optional step. Some people might skip it, but it's just for the sake of making the notes more readable. Inside the parentheses, I'm just going to get one fraction. So I can drop that parenthesis, write 1 over h, multiplying the one fraction we're going to get. We have a common denominator down below, so we get to just copy it. X plus h minus 1 times x minus 1. And then we're subtracting across the numerator. I'm just going to copy that in, and we'll do that simplifying on the next step. X plus h times x minus 1 minus x times x plus h minus 1. And notice these parentheses, if we didn't include them, the word could get extremely foggy from here on out, because those parentheses allow x to distribute into all three terms. Parentheses here require us to FOIL it out to get the right answer. And this problem always has a built-in check. If that h doesn't cancel the 1 over h, then we have a problem. Something didn't quite go right. But now we're at the just crank it out portion of the algebra. You're going to get a really, really long fraction bar. And when you multiply a fraction, 1 over h, times this big fraction, you just multiply through the denominators. I would always write it like this: h, x plus h minus 1, times x minus 1. And you never want to distribute this out. It would overcomplicate it, make it harder to simplify the whole fraction. But what we do want to distribute out is the numerator. We need to recombine it as much as possible. So I'll start right here, distribute x in, and we'll get x squared minus x. Now move over to h, distribute h into x minus 1, and we'll get plus hx minus h. And last bit, negative x distributes inside, and we get negative x squared minus xh plus x. I think I got a little carried away with the fraction bar, but we can leave it as is. So if everything is going according to plan, that h is the one we're really looking at closely. It has to disappear somehow. And that means everything in the numerator that doesn't involve h as a factor has to die. So that positive x had better go away, or else I'm not canceling that h at all. But notice there's a negative x to be canceled right away. It has an opposite pair immediately. Likewise, x squared can combine with negative x squared. Those are gone. And even though it didn't have to cancel, hx cancels with negative xh. Commutativity of multiplication says x times h is the same as h times x. So those are gone. And I cleaned up a lot. The only thing surviving in the numerator, I want to circle it so I don't lose it, is just negative h. You can cancel it right here if you'd like. I'll put one more step in for the notes, so it's, again, a little bit more readable. We have negative h, division by h, x plus h minus 1 times x minus 1. Finally, we have a cancellation going this way. Now, it doesn't mean nothing's in the numerator any longer. There's still a negative 1. So you could put a 1 here just as a reminder. I think a lot of people cancel and they just leave it like that. That's not harmful either. Just whatever helps recall. Negative 1 still emerges from the top. And from the bottom is x plus h minus 1 times x minus 1. Finally, this is the simplified form. You don't have to expand the denominator. It's a lot of work for no benefit. I would just leave it exactly the way it sits right there. Definitely a nasty one. It's the challenge question from WebAssign. The one that you have in the homework is not as bad, or excuse me, in quiz 2 is not as bad as this one. Well, any questions at all, folks, on marching through this problem here? Sorry, say again. We've pretty much calculated the slope of this line as the points overlap altogether. So if I let h go to 0 right here, I have now the derivative of that original function. So it's going to give me the instantaneous rate of change at any value x we would have put in. Does that make sense there? Gotcha. So if h was, say, a 0.1, we're looking at this graph. X plus h and these two dots are close to each other. but we want h to get smaller and smaller and smaller. And so even though we didn't do that step, this right here is one step away from the so-called derivative that you mentioned. So that's what we're essentially calculating. Well, other questions or comments so far? Okay, well, we got through the meaty part of these notes. It's a lot of algebra we had to get through. The next portion is a little bit more fun. It's about increasing, decreasing functions, as well as things about minimum and maximum values. Most of the problems in ALEKS are just graph type problems, but I brought the same kind of stuff in for the notes today, so we can have similar type of work. Let's start with these definitions here for increasing versus decreasing functions. I will solve it using this graph right here. It's pretty clear this one came right out of ALEKS. And so when we go to solve this one, you're going to see problems where they give you just some random graph. This A, B, C, D, E, those are just points on the graph itself. And we want to know when the graph is increasing, constant, or decreasing. The technical definitions are here. It says a function is increasing on an open interval if the function values increase, f of b is bigger than f of a, whenever b is bigger than a. That's a nice technical definition. But honestly, when you read through that, without a picture, it's kind of tough to see what they're saying. This is the better way to view it, I'd say. Always read your graph going left to right. And if the curve is going upwards, it's got to be increasing. If it's flat or constant, if it's going downwards, we have a decreasing function. So that's the main takeaway for these two definitions right here. Visually, it's pretty easy to spot once we practice it. So let's give this a try, going down the line. It says between points A and B, are we increasing, constant, or decreasing? Sorry, say again, did you say? Exactly, we're going to be increasing. And when they say between points A and B, we're saying here to here. Does that make sense to folks so far? Okay, then from B to C, well, that's when we're constant. The curve isn't changing in any height. So we have a constant there. How about from C to D? Any volunteers on that one? Exactly. The curve is going downwards, so we correspond that with a decreasing. And finally, it says from D to E, well, the point has to go up as we go left to right. So it must be increasing on that range there. That's kind of relaxing almost. Would you agree compared to what we've just done? Not too bad. Awesome. So there's a few graph type problems just like this in ALEKS. I think they're not too bad to get through. If you have any questions about them, please don't hesitate to ask. Well, let's try another one. We're looking at increasing functions, decreasing functions. And the next would be maximums and minimums. Here it does get a little bit tricky because we're going to have two different flavors of maximums and minimums. And the first one are absolute max, absolute minimum. If we say an absolute maximum, we mean a point on the graph that's taller than everything else in the graph. The way they say it here, an absolute maximum is a number like f of c, whenever f of c is bigger than all the other function values for all x in the domain. Now, the thing that's tricky here is whenever we say absolute maximum, the answer is the output. That, in my opinion, deserves an exclamation mark. The absolute maximum is the height. It's not the x value on the x-axis. It's the height of the curve on the y-axis that we have to give. So this c here is just the location where the maximum occurred. F of c itself is the absolute maximum. That's tricky enough. Let's practice this right away. Same idea with absolute minimum. A minimum would be a number, an output, that's less than or equal to f of x. In other words, smaller than all the other function values for all x in the domain. So let's practice this here. We have two graphs, a graph of g, graph of h, shown. For each graph, we're going to find the absolute maximum and absolute minimum. But watch out for this when you do these in the homework. This one's a little bit tricky. I don't want to do red. That usually means I have a revision. Sometimes there is no absolute maximum or there is no absolute minimum. Just depends on the function. Well, let's first take a look at the graph of G. When we look at this dashed line is just telling us there's a vertical asymptote. It's not part of the graph, but it's helping us understand it. This arrowhead is saying the graph is going down forever, according to that dashed line. They printed it a little bit odd, but they're allowed to because they put an arrowhead on there. And also be very wary of closed dots versus open dots. That's always extremely tricky in my opinion. Well, as we look at this, let's focus on the maximum. Anyone see what number would be the absolute maximum of this problem? Exactly. I like how folks are saying 3. The maximum is right here. The way you get to it is you had to plug in a -2, but that's not the maximum. That's just the location or the address to get to the maximum. The maximum itself is actually 3. So 3 has to go here. I'll put an arrowhead because the box I have when I took a screenshot from Alex is just too small. Well, let me try before I give up on it. Yeah, that's not readable. I'll just use an arrow to point to where our answer is going. Does that make sense on folks for absolute maximum? Awesome. A good eye, that's the absolute maximum because where the red dot is, that's the highest dot on the entire graph of G. Now, how about minimum of G? Good call, folks. -50 is not a bad answer. I don't think they'll allow us to accept that or input that into Alex, but I'd say none is probably the better answer on this one. Extremely tricky, right? If I looked at this, I might have said -5 is the absolute minimum. That's impossible. There's an open circle there for one. Even if it was a solid circle, it's still not the absolute minimum because this curve is still going down. It's going down forever off the page, attracted to that vertical asymptote. This graph is just printed in a really tricky way, in all honesty. So watch out for arrows, watch out for open circles. On this one, our answer is none. Does that make sense to folks on this one? Okay, so this is a weird problem. It's one of those situations where it might be easy to eyeball some of these, but if we miss the tiny details, like that arrow going down, it's easy to miss that there is no absolute minimum at all in this graph. With those ideas in mind, let's do it again. Here's the graph of a function called h. So you could call this y equals h of x if you wanted. Anyone see the maximum value of this h? It'd be 3 again, absolutely. This is the highest point, and so the absolute maximum is the output value, 3 again. How about absolute minimum on this graph? Good call. This one has no tricks. They put a solid dot just to let us know that we're definitely are getting as low as -4. So -4 would go right there. And even if they didn't put a solid dot, if it was just a curve that went through, dipped, and came back up, we would have still considered -4 as the correct answer on that graph. So we did it, folks. H was the nicer function. G was nobody's friend. It has issues, and they absolutely printed it in a weird way. Watch out for those arrows as well. Yeah, go ahead.
Just to clarify why the absolute minimum is none on that one, it's because there's an open dot, so -5 isn't included with, I guess with that section.
Yeah, exactly. There's no actual point right here. Exactly.
And then that arrow is continuously going down, so there's not any specific minimum because it's continually going down and there's an infinite amount of them, or?
Yeah, it's getting more and more negative values, unbounded. Exactly.
Okay.
Yeah, go ahead.
I don't know if they do it. What if, like, let's say the graph of G, instead of being infinite on the end, what if it had like an open circle at like -4?
Oh, so open circle right here?
Yeah.
That is a really good question. I'm glad you asked that. So this graph turns into be something that's more tricky than any of the original ones. Let's answer it in this way. If we had a graph that looked like this, we want to know what the range is, right? Sometimes finding absolute maximums, absolute minimums, range is a good way to think about it, especially on this tricky situation. So If I'm giving the range, I go to the smallest value I see down here. It corresponds to -5, but open circle says it's not actually a point on the graph, right? It's parenthesis -5 on this version, and it goes all the way up to the absolute maximum of 3. Now, this is weird because on one side I have the open intervals. On the other side, I have the closed bracket. I don't know how to put a bracket, should probably not try, but that means it's half open, half closed. This is in actual mathematics called a clopin set, open and closed. But around -5, the kind of numbers you get here are, say, -4.9. That's one of them. We're getting really close to -5. Can you find a number smaller than -4.9 inside that set? Absolutely. Do you have a version? Exactly. That's even smaller. Can we do better? Yes, we can go -4.99, or even smaller is 99. Well, that game doesn't end, does it? Every time you make this a little bit smaller, and you can, with the open set, there is always headroom. You're getting smaller and smaller and smaller, but that never ever stops. It doesn't stop at -5 because it's not even in the set. This still has none for absolute minimum if the graph looked like that. Really weird situation for sure. And open sets and closed sets, they're a lot weirder than you think. So always keep that in mind when you're doing domains and ranges in interval notation. But does that answer your question there about that situation? Awesome. Other questions at the moment? Okay, I'm going to delete this only because we changed the graph, so the range is no longer the same. But for that original comment, it'll be alive in the video if you go to track it down. Well, those are absolute maximums, absolute minimums. And the next thing we want to take a look at is local maximums, local minimums. So there's a new flavor of all this. You have a local maximum whenever, let me just move this down so it's more readable. We can find an f of x that's going to be, we'll find a local maximum f of b is a local maximum if just nearby b, not on the entire graph, but just nearby, f of b happens to be larger than everything else. Or we'll find a local minimum if f of b is smaller than all the other values nearby. So for this example 6, we're going to find all local maximum and all local minimum values of the function g. This one is a little bit tricky. If you're solving something that involves local, one good idea is take out a couple note cards. You want to cover up the graph strategically. I'll be using this marker right here to cover up the graph. So I want to find all local maximums and all local minimums. I'm going to go left to right, starting right here. Well, there's an open circle. This is related to the comment you made before. There is no local maximum whatsoever there. Does that make sense to folks? Awesome. So we omit the local maximum, but then something is happening for sure nearby 2. There's an open circle, but the function is defined down here. Would you call this a local maximum or a local minimum? Definitely a little bit trickier, right? Well, let's maybe cover up something about the graph. If they're saying local, I only care about the graph when x is nearby 2. So I'm going to go like this and like this. Pretend that's my graph now. Would that be a minimum or a maximum? Exactly. It's a minimum because this point right here is smaller than every other f of x value. Those values just get larger and larger on the left and the right. So we have a local minimum right there. We could say local min, it's f of 2, which is equal to, let's see, at a height 1, 2 units. The actual value we plug in, say if we're doing an Alex problem, is the 2. The f of 2 is just for the sake of the notes. We started at 2, got to there, and that's our minimum. So locally nearby, that's what the local min is. Now let's take a look at what happens around 3. If we're around 3, let's go up to the graph. Does that feel like a maximum or a minimum locally? I agree, that one has to be a maximum. It's not the absolute maximum because go over here and there's things that are higher. If you're only thinking locally around 3, yeah, that looks like a maximum on the curve right here. And it's at 1, 2, 3, 4 units high. Yeah, go ahead.
So is it just basically like the axis of like a curve and a concave curve?
Essentially, yeah, if you go up like this, you have a local maximum. If you go down like that, you produced a local minimum. Absolutely. And there's other weird ways for that to happen, like when there's an open dot and things drop down. But that's a great way to think about it. Anytime anything goes up like that, you're thinking maximum. Anything goes like that, think minimum, and you're in great shape. Other questions so far? Okay, so let's finish off this one and say local max. We found one at f of 3 equals 4. Highlighting the yellow just to mention, again, you have to give the answer of 4 as the official answer on that one. So now let's keep on trudging through this. Now we're at 4. Only care about local values, so I'll let the graph look like this. That was a little bit too aggressive. Let me try again. What does that look like to folks? Min or max? Absolutely. So here we'll say that this one is a local min. So f of 4 equals 1. And well, we just keep on going. Next one. Let's see, as we keep on going, nothing interesting until, like you said, we have that shape. Right where the red dot is, locally, we have a maximum. Do folks agree with that at the moment? Awesome. So I'm at 1, 2, 3 units high, and we can say f of 6 equals 3 for our local maximum. Now we are ready for the worst part of this graph. If I looked at these definitions and I didn't look too carefully, I would have called that a local minimum. But here's the problem. Let me add this to the notes. There has to be an interval around the value of 7 here. I need to find numbers bigger than 7. Say we could go down to 6. That would work. I'd be going slightly to the left. I have to be nearby 7. But now here's my trouble. I can't go to the right. The function just stops right here. We would have left the domain. You have to be on the left and the right around this point to get a local value. So if the curve went like that, that's a local minimum. But if it ends like that, it's a massively horrific trick question. So let me put this as the last piece of advice when you see these. Local max min values. Let's add some extra space here. Local maximum values never occur at the boundary of the domain. 7 is right at the boundary. There's no larger function values beyond that. So this one is sadly nothing. It's not a local max, not a local minimum. Neither is it an absolute maximum nor an absolute minimum as well. So watch out for those if you're dealing with locals. You don't care about what happens here. Even if it was filled in, it wouldn't be a local maximum. It would have been an absolute maximum. But local is really very specific. Well, any other questions, folks, about getting through these? Okay, well, we went right to the minute. Sorry about that. I usually like to have a little bit more time for questions at the end. Any last questions then before we call it a night? Oh, it's down like there. Gotcha. Sorry about that. Well, have a great night, folks. If you have questions, I'll be happy to help out. Otherwise, I'll see you all on Tuesday. Have a happy Labor Day, but sadly, we're unaffected. Business as normal Tuesday for us. There'll be no class on next Monday, yeah. So if you have a Monday class, it's officially canceled. Well, shouldn't have been scheduled in the first place, really.